Welcome to today's lesson. In this first tutorial, we will attack the first two objectives. The student will be able to describe an arithmetic pattern, and we will be able to use the two arithmetic formulas. So we are in section 12.1 and 12.2 in our Algebra 2 textbooks, and we're looking at sequences and series, specifically in this set of sections, arithmetic sequences and series. A sequence is simply a set of numbers separated by commas that share some sort of pattern. When we're talking about an arithmetic sequence, each term is found by adding a constant called d, and that d is called the common difference, to the previous term. I always remember that arithmetic sequences are adding to get each term. You have the double A. So in our first example, we have 32, then 38, then 44, and you can see that we are in an arithmetic sequence where we are adding 6. And since we continue to add 6 to get from term to term, D must be equal to 6. And that's good to know. It's always helpful to go and find what the common difference is, the D. So we have 4 questions I'd like to ask about this. The first one says, find A sub 1. A sub 1 is the symbol that we use to represent the first term. We use little subscripts to name our terms. Well, A sub 1 is simply our first term, and that's 32. Part B says to find A sub 6. A sub 6 would represent our sixth term. Now we only have 3 terms, and to be able to find the sixth term, well, it really wouldn't be too bad to just continue to add 6 3 more times. So if we add 6 again, we'll have 50, and then we'll have 56, and then we'll have 62. It's really not that difficult. This is called the brute force method, when you're simply just adding to get to a certain thing. Sometimes brute force will be the way to go because we're only looking for, a little term. If we were looking for the 712th term, though, I don't imagine you'd want to add 6 a bunch of times, that many times. But to find A sub 6, it's really not too bad. 1, 2, 3, 4, 5, 6. Yep, here's the sixth term. It's 62. So that's not too difficult. Before we find something that's a very large term in this sequence, the 712th term, even maybe the 50th term, it might be more beneficial to have the formula for any term. We call that A sub n. A sub n represents the last of n terms. So if we could have a formula that A sub n is equal to for this sequence, that would be quite helpful. So let's turn over to that formula, and then we'll come back and attack parts C and D. There's the first of 2 formulas today, which is the formula to find the nth term, any term of any arithmetic sequence. The nth term will always be the first term, A sub 1, plus the number of terms take away 1 times D, the common difference. And this is the first of the 2 formulas we're going to look at in this tutorial. Let's label our terms. A sub n equals the nth term. Let's label our symbols, I should say. A sub 1 represents the first term. N represents the number of terms that you're talking about. And D is the common difference. That's that number that you're adding to get from term to term. So if you have those items, you can plug into this formula. It's helpful that this formula will be given to you on the formula sheet for our SOL state test. But for right now, let's go ahead and use that formula in this tutorial. So A sub n will always be equal to A sub 1 plus n minus 1 times D. Well, let's see if we have this information. A sub n for this example, A sub 1 was 32. The number of terms that we're talking about, okay, well, we don't really know which term we're talking about, so I'll just keep that as n minus 1. And then D is 6. So this is the formula that we'd be using to find any term. If I plugged a 1 in for n, then I would have 1 minus 1 is 0. 0 times 6 is gone, 0, and 32 would be my first term. If I plugged in a 6 for n, 6 minus 1 is 5. 5 times 6 is 30, and 32 plus 30 is the 62. So this formula does work, and it can help us over here to find the 712th term. If we're looking for the 712th term, I'll plug into my formula, which is going to be 32 plus 712 minus 1 times my d, which is 6. When I plug that into the calculator, I get that my 712th term is 4,298. So it's a whole lot more helpful when we have a formula to find such a large number in our arithmetic sequence. Okay, so example number 2, let's review. Write the rule for the nth term. That's just another way of saying a sub n, the nth term of this new sequence, and use it to find the 125th term. Okay, so we have a new arithmetic sequence, 16 to 7 to negative 2. Now, what are we adding to get from one term to the next? This sequence is a decreasing sequence, so we must be adding a negative. And it looks like we're adding negative 9. Adding negative 9. So it looks like d is equal to negative 9. Remember that we're always going to be adding d. So watch out if it's a positive or if it's a negative. Okay, so a sub n, I'm just plugging right into this formula, will be a sub 1, which we know is 16 since that's the first term, plus the number of terms, take away 1, n minus 1, times d, which is a negative 9 in this case. So this is my rule for my nth term. Now let's use that to go and find the 125th term. A sub 125, now I know that n is 125, will be 16 plus 125 minus 1 times negative 9. Understand that your order of operations say that we have to deal with this set of parentheses first. 125 take away 1, of course, is 124. Then we can multiply these numbers together and then add 16. And ultimately, our 125th term, or a sub 125, will be negative 1100. So we wrote the rule to find any term. We just needed to know what n is, and then we used it to find when n is 125, what's that 125th term. Let's flip over here. Another question that they're going to ask you on your state test, example 3, it says find the two missing arithmetic means. And what this means is to find the two missing numbers in this pattern such that the entirety of this would be an arithmetic sequence. So a pretty easy way to deal with this is to understand that whatever this number is, I know that I'm going to find it by taking whatever d is and adding it to 5. So it makes sense that this number would be 5 plus d. Now, I don't know what d is yet, but I'll find that. And if this is 5 plus d, I would take d again and add it to that to get my third term. So this would be 5 plus d again, or rather 5 plus 2d. So I'm adding d, and then I'm adding another d, and then I would add yet another d to get to 26. So if I'm going to add another d, that would become 5 plus 3d. And knowing that is how I'm going to solve this question. I know that 5 plus 3d must be equal to 26. And there's an equation that I can use to solve for d. If I subtract 5, I have that 3d is equal to 21, and therefore I now know that d is equal to 7. And obviously that's very helpful because once you have d, it's pretty easy to find any term in our arithmetic sequence. So if d is 7, then 5 plus 7 would turn into 12, and then 12 plus 7 would turn into 19, And then 19 plus 7 would turn back to the 20, or would not turn back to, but would turn into the 26. And I have just solved my problem. The two arithmetic means are 12 and 19. We're kind of finished with arithmetic sequences. I want you to understand that an arithmetic sequence is when you have a bunch of terms separated by commas. Oops. Dot, 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 dot. We can continue that on forever. An arithmetic series is when you take those terms and add them all together. So an arithmetic series is when you're taking the terms and putting plus signs in between them and actually adding them all up. There's a famous problem, which is here in example 4, which I always like to do this because it helps me to remember the next formula I'm going to show you. And that problem is to find the sum of the first 1,000 positive integers. So what we're trying to do is we're trying to take 1 plus 2 plus 3 plus 4 plus dot 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 all the way to plus 997 plus 998 plus 999 plus 1,000. It might seem like this is going to take a long time, but that's just because that's how the terms are grouped. This is really an inefficient way to group the terms if we just group them in order, 1 plus 2 plus 3 plus 4 plus 5. There's a bunch of different patterns of numbers or patterns of sums throughout this problem, but the most efficient way to actually group these terms, perhaps, is this. Take the first term and the last term and add them up, and you would get 1,001. And then take the second term and the second to last term and add those up, and you'd get another 1,001. Take the third term and the third to last term, add them up, and guess what? You get another 1,001. Each one of these pairs adds up to 1,001. So the question is, how many pairs are there? Well, if you have 1,000 terms, then that must mean that you have 500 pairs of 1,001. And that sum would be 500,500. And that is our answer. The mathematician who came up with reorganizing these terms into a better order got to the answer a whole lot faster. And I like to remember this problem when I'm trying to remember this formula. Our second and last formula of this tutorial is the sum of any finite, that means that it has to stop, the sum of any finite arithmetic series. I'm going to label that with a big S for sum, the sum sub n of any finite arithmetic series. You take the number of terms that you're trying to add up and you divide them by 2, and then you multiply that to the sum of the first term plus the last term. And that is the sum formula. And that's exactly what the mathematician who reorganized the terms in that previous problem did. The 500 came from taking the 1,000 terms, dividing by 2, there's the 500, and then the first term, which was 1, plus the last term, which was 1,000, is where the 1,001 came from. So a pretty useful formula. Example 5 says, find the sum of the first 23 terms, S sub 23, for this sequence. Or excuse me, for this series. This must be a series because I see the plus signs. So let's confirm that this indeed is an arithmetic series. I must be adding something that's the same thing. -4 to 1, I believe that's adding 5, and we continue to add 5, yes. So this must be an arithmetic series. So if I want to find the sum of the first 23 terms, let's see what I need for my formula. I need to know how many terms. Well, that's easy. That's 23. I need to know what the first term is. Well, that's easy because that was given. It's -4. But I also need to know what the last term is, or rather the 23rd term. So it looks like I have some work to do. I need to find a sub 23 before I can plug into my sum formula. So this is actually going to use the previous formula. A sub 23 is going to be A sub 1 plus 23 take away 1 times D. But I already have this information. So A sub 1 was -4, or is -4, here it is, plus 23 minus 1, well, I'm going to just change that to a 22 now, times D, which we just found was 5. So it looks like A sub 23 is going to be 106. 22 times 5 is 110. Take away 4 is 106. So now I know everything I need for my sum formula. S sub 23 is going to be the 23 terms that I'm adding up divided by 2, multiplied to -4, which is my first term, plus 106, which is my last term, or my 23rd term. And that came right from here. Plug all this into your calculator, of course watching your order of operations, and it should get a sum of 1,173. Thanks for watching this tutorial explaining the first 2 formulas for our sequences in series, and I'll see you in the next tutorial and in class. Bye-bye.